Hello, students, and welcome. I am so incredibly excited to dive into this explainer today because we're looking at the literal magic happening all around us every single day. You know, chemistry isn't just something locked away in a sterile lab with folks wearing white coats and safety goggles. No, it's this dynamic, constant force that actually shapes our world, and today we're going to decode exactly how it all works.
Just think about your daily routine for a second. Have you ever actually wondered how these totally ordinary changes happen? Like the moment we leave a bowl of milk out overnight and it turns to curd. Or when we strike a match to light a candle. And what about leaving an iron bike outside in the rain, only to find it completely covered in reddish-brown flakes a few days later? Now, these might just seem like basic facts of life, but they're actually profound transformations happening right before our eyes.
See, what's going on here aren't just simple physical shifts. They are chemical reactions, forming entirely new substances. In every single one of those everyday examples, the materials we started with completely altered their fundamental identity. And really, that's the very definition of a chemical reaction. It's this incredible process where substances change at the molecular level, leaving us with something that has completely different properties than what we originally started with.
So to really wrap our heads around this, we're going to cover 5 key topics today. We'll start with chemistry in everyday life, then look at how to actually spot a chemical reaction. After that, we'll learn the language of chemistry, break down the 5 types of reactions, and finally, look at oxidation in the real world. Let's get to it.
All right, Section 1, Chemistry in Everyday Life. Let's look at the basic ingredients of these changes.
Let's take that milk turning into curd example again. The milk is our starting ingredient, what we call the reactant, over on the left side. And that newly formed curd, that's our product, on the right. It really is that simple. Reactants are just the substances taking part in the reaction, and the products are the brand new substances formed after all the magic happens.
Moving right along to Section 2, Spotting a Chemical Reaction.
So how do we actually play detective and prove a chemical reaction took place? Since atoms are way too small to see, we have to rely on macroscopic clues. There are actually 5 physical signs you can look out for. First, a change in color, like gray iron turning into reddish rust. Second, a change in temperature. For instance, mixing quicklime with water produces some serious heat. Third is the evolution of a gas, like when you mix vinegar and baking soda and get all those fizzing bubbles. Fourth, the formation of a precipitate, which is just a fancy way of saying an insoluble solid magically appears when you mix 2 liquids. And fifth, a complete change in state. If you spot one or more of these signs, boom, you've caught a chemical reaction in action.
Let's move into Section 3, the language of chemistry.
Now, it is honestly so fascinating how scientists write this stuff down. If we had to write out magnesium reacts with oxygen to form magnesium oxide every single time, it would literally take forever. So we translate that bulky word equation into a short, elegant chemical equation using symbols. We use Mg for magnesium, O2 for oxygen, and an arrow that simply means yields or forms. It's this brilliant, universal shorthand that any scientist anywhere on Earth can instantly understand. But hold on, let's look a little closer at the numbers here. If we count the atoms in our magnesium equation, we actually run into a bit of a problem. We have 1 magnesium atom on both sides. Totally fine. But check out the oxygen. We've got 2 oxygen atoms on the left in our reactants, but only 1 on the right side in our products. This means the equation is not balanced. We are literally missing an atom of oxygen. And here is the absolutely crucial point. We have to balance the equation because of an inescapable rule of the universe called the law of conservation of mass. This rule states that matter can neither be created nor destroyed during a chemical reaction. Atoms don't just magically disappear into thin air, and they definitely don't pop into existence out of nowhere. The mass of the reactants absolutely must equal the mass of the products. So, how do we fix it? By adjusting the equation to 2Mg plus O2 yields 2MgO. This beautifully illustrates a perfectly balanced scale. We just added coefficients, those big numbers in front of the symbols. So now we have exactly 2 magnesium atoms and 2 oxygen atoms on the left, matching up perfectly with the 2 magnesium and 2 oxygen atoms on the right. Order is restored, and our universe is in balance.
All right, jumping into Section 4, the 5 types of reactions.
Not all reactions happen exactly the same way, right? Scientists categorize them based on how those atoms rearrange themselves. First up is the combination reaction. This is where pieces join together to form a single product, just like our magnesium oxide example we just looked at. You basically take two distinct substances, they combine, and they become one completely unified compound. Next is the decomposition reaction, which, you guessed it, is the exact opposite. Here, a single compound, like water, breaks apart into simpler substances, like hydrogen and oxygen gas. Think of it like taking a complex structure and deconstructing it right back into its basic building blocks.
Then we have the displacement reaction. This is where a tough, more reactive element, like zinc, comes in and literally kicks out a weaker element, like copper, from its compound. Zinc pushes the copper aside and bonds with the sulfate to form zinc sulfate, leaving the poor copper all by itself. It's essentially a chemical game of musical chairs.
Our fourth type is the double displacement reaction. This one is like a dance, where two compounds completely swap their ion partners to form two entirely new compounds. Notice how barium pairs up with sulfate and sodium pairs up with chlorine. Everyone swaps, resulting in a totally new set of chemical couples.
Finally, our fifth type pairs oxidation against reduction. Now, these always occur together in what we call redox reactions. Oxidation is simply the addition of oxygen, or the removal of hydrogen. Reduction is the exact reverse, the removal of oxygen or the addition of hydrogen. Because they work together in tandem, whenever one substance gets oxidized, another is simultaneously being reduced.
And that brings us to our final topic, Section 5, Oxidation in the Real World.
Let's zoom back out to the macro level to see the real-world consequences of oxidation on our daily lives. Unfortunately, oxidation causes corrosion, like the rusting of iron. This progressively weakens metals and leads to massive economic losses globally. Whenever iron is exposed to oxygen and moisture in the air, a redox reaction kicks off. So the gradual destruction of bridges, cars, and buildings due to rust, that's a direct result of this inescapable chemical reaction happening right in front of us.
But oxidation doesn't just eat our bridges. It also messes with our food through a process called rancidity. This is what causes oils and fats to develop a seriously unpleasant smell and taste if they're left out in the open. If you've ever opened a super old bag of potato chips and noticed a stale, almost paint-like odor, yep, that's rancidity. The fats in the food have literally oxidized.
But hey, fortunately, we can use science to our advantage to stop this. By understanding the reaction, we can prevent rancidity. We can refrigerate food to slow the reaction down, use airtight containers to cut off the oxygen supply, or, and this is a really cool trick chip manufacturers use, we can pack the bags with nitrogen gas. That way, there's literally no oxygen available to cause the oxidation in the first place.
So, bringing it all together, understanding these principles really proves that chemistry isn't just locked away in a laboratory. It's the digestion of the food in your stomach, the cooking of our meals, the photosynthesis keeping the plants in your window alive, and the very breath entering and leaving your lungs right now. Everything is connected through these fascinating, perfectly balanced reactions.
So, as we wrap up this explainer, I want you to think about your own daily routine. Look closely at the world around you. What is one chemical reaction you observe regularly? And which topic today did you find the most interesting? The more you look, the more you realize that the absolute magic of chemistry is happening everywhere, every single moment. Keep exploring, stay curious, and I'll see you in the next one.